All right, everyone, we are back and we're going to go through our last exam problem. So I'm going to quit everything here. I'm going to start fresh. There we go. And then let's go ahead. I'll need to move back up once this goes through. But let's look at our question. So we're dealing with a controller. Here's our no noise, no disturbance. Here's our controller. It's a PI controller. This is a third order system. So first, when you figure out is the plant stable, you're going to use Ruth Hurwitz. We're going to determine the control parameters that will indeed stabilize the whole system. So the plant stability first, then we'll get that. Then we're going to tune this particular plant here with cord decay method. And then finally, we have some conceptual questions actually we can answer right now. So KP, we know that that is tied to increasing essentially the effective stiffness of the system. So as KP increases, we should expect omega n to increase. And then in terms of our time domain specifications, we know that TS is equal to 4.6 over sigma, which is equal to 4.6 over omega n times our zeta, which is our damping ratio, which is equal to 4.6 divided by square root of k over m times c over 2. So let's go ahead and zoom out. Over 2 square root mk. So our k's cancel out here. Our peak time is equal to pi over omega n. And then we also know that our rise time is equal to, 1.8 over omega. I believe that is true. I always have to recheck those. Luckily, I think we're in the right spot. Yep, our rise time. Oh, no, see, TP is over pi over omega. Okay, so let's go. That's not the exam. Actually, yeah, this is the exam. So let's go. TP is equal to pi over omega. And then this is 1.8 over pi omega n. Excellent. And then we also know that our overshoot is equal to exponential minus pi divided by, or times zeta. Zeta here over square root 1 minus zeta squared. So increasing Kp will increase the natural frequency, yes. Increase oscillations, yes. Increase the settling time, no. And reducing the overshoot, if I increase K, then what happens? My zeta becomes smaller, my overshoot becomes worse. So those last two statements are not true. Decreasing KT will decrease the rise time. So if I decrease, KD is effectively my effective stiffness terms. So as KD increases, my zeta increases. So I don't see a huge impact on the rise time and the peak time in terms of KD itself. It will and should have an impact on my settling time. So it should reduce settling time significantly. So makes sense because we're damping out those. So there's nothing essentially related here. It should actually. There's nothing really about steady state air, but I increase my settling time, so actually should decrease steady state air. So that's not true. Ki will increase the rise time. Nope. And overshoot actually should reduce the overshoot because, again, reduces steady state air. Excellent. So let's go ahead. Hopefully my Mathematica is awake now. And we can go into my controller is going to be equal to Kpt plus Ki divided by S. My plant is S minus 1 over S cubed plus 5S squared plus 10S minus 5. So that's our plant. I want to look at, is this plant itself stable? So I need to actually go up here, way up. I need to shift enter all these cool functions. And I think it should be good to go. So now let's go down. I'm just going to move. I'm moving up here slowly. Let's go. Here we go. So I've got my Ruth table. So I can say 1, 5, my coefficient's 10, minus 5. Are we stable? No. So the plant itself is not stable. So hopefully we can make our entire system stable. So now I've got my closed loop transfer function. And what we can do now, I don't know why it's showing it like this. There we go. I'm going to take this and expand it out. Expand all here. Excellent. So now I can look, this is a nasty looking system, but 5, kp plus 10, ki minus kp, and then minus 5, actually minus k, it should be ki minus kp minus 5, and the last one is just minus ki. All right, so now we can get our reduce. So let me just make sure we've got that. S minus 1, s cubed, 5, s squared, plus 10s minus 5. Kp there, good, good, good. And now we've got our values. So let's go ahead and reduce. So I need this to be greater than 0. I need this to be greater than 0. And then I need this to be greater than 0. Meaning I'm going to actually have to have a negative controller. All right, it's KI. I'm just going to double check. 1, 5, Kp plus 10, Ki minus Kp minus 5. Yes, here we go. Value here. And there we go. We have our conditions here for Kp and Ki. It needs to be less than 0 and between here. So we've got our conditions. Excellent. So we found those that will satisfy essentially the plant. Now we have another plant function. So I'm going to say PS_tune. My PS_tune is going to be as follows. So I need to tune it, and I'm going to say my CS is going to be equal to Ki, or actually Kp plus Ki divided by S plus Kd times S. So this is going to be my CS. My PS_tune is going to be equal to 1 divided by S plus 1, S plus 2, and S plus 4. And then my GS_tune is going to be equal to CS times PS divided by 1 plus CS times PS. But it needs to be PS_tune everywhere here. Good. And then we're also going to say slash dot again. I'm going to take I'm going to look at the system here, and we're going to say that slash dot Ki goes to 0 and Kd goes to 0. Excellent. Let's just do full simplify. And then we're going to say our Rs is equal to 1 over S. So now my YS_tune is going to be equal to inverse Laplace transform of GS_tune times RS STT. And it's going to look nasty there. We don't want to deal with that. So instead, what we want to do is look at our pole zero simple plot. However, we do want to see, so what values of here, let's look at our Ruth, let's do expand all actually. So let's get stability first. So I need my Ruth table. So 1, 7, 14, 8 plus Kp. We can look at those values, both, or actually table form. So we need to make sure that here we are going to be equal to reduce. So we're going to say this has to be greater than 0 and this has to be greater than 0. little easier than the last one. So we just need to be between here and 90. So if we do pole 0 simple plot of GS tune, actually we need to do transfer function model GS tune S, and then we're going to do one more thing, GS tune slash dot. Let's say KP goes to, let's say 10. Okay, so it looks like we're in a decent, we're going to look like, again, some oscillatory response, which will be perfect for the chord decay method. We can't use, essentially, again, this is not Ziegler-Nichols, so let's go ahead and let's work through the tuning. So now I'm going to say YS tune. So I'm going to say Y test equals YS tune slash dot KP goes to what I said here, 10. So let's go ahead here. And then I'm going to say plot Y test T from 0 to 10, comma, plot range all. And so we're going to need to see a little bit more. So we're a little bit too damped. So what if we change this to 1? Let's say 1 here. Oof. Actually, we need to go higher. So let's go. All right, now let's try 40. So when we look at a KP of 40, we can see, all right, now we can look at some peaks here. So we need to be looking at the 0.25 value from our steady state, which, let's go ahead and look at that right now. So Y test slash dot T goes to large value. Let's look at that numerically. And we're going to see 0.833. So right now we have peak, let's call it 1.26. So 1.26 minus 0.8333. And then we want this divided by, and it's still going to be this steady state value here. So let's put it in here. And then our second peak value looks to be about 0.97. So let's do 0.97. Let's see if we hit our magic 25. Oops. Magic 25 number. So a little bit large. So let's go to 30, perhaps. So let's go ahead. Let's look at our 0.7894. So I'm just going to put these in here. And then 1.1. 1.1, 0.85. So let's see, 0.85. Of course. So probably around 35. Let's see. Let's do one more just to get us a nice value here. Here's our steady state, but we're getting pretty close. And then now 1.19. And then what do we got here? 0.91. That's pretty close. All right, so this is now our ultimate gain. Our KU is going to be 2 times this value, which is 35. So we've got that. And then now, let's actually scroll down. I need my Ziegler-Nichols. Not my Ziegler-Nichols, but I need my tuning equations. Where are they? They're somewhere in this notebook. So let's look for our tuning. Where are you, tuning? Actually, where's our tuning equations? Here we go. So here's our tuning parameters. And actually, we can go ahead and almost copy this code a little bit. So I'm going to copy this here. We're going to go back to our expressions here. So that's our KU. We need our period as well. So we need the period of this, which will just be, let's get coordinates. So I'm going to say here, I'm going to say here, Control C, Control V. So my period, TU, is going to be equal to this minus this. This minus this. That's our ultimate period. So now we have our equations here. Here, actually, we call it period. here, here, here. Our new GS, we'll just put that, and actually we'll put, so we had our PS tune. I'm going to say GS, I'm just going to say GS equals this. So now that's our G of S. We can go down here. So now we got the values here, except now we're just saying KP substitutes, KI substitutes, and KD substitutes. Here, new GS here, T from 0 to 10, and that looks pretty nice. So that's our system response. So we'll see you all in the next video. Actually, that's the end of the exam. So we'll see you for the next exam and for problem set 9 and for exam 3. Thanks. Bye.